So hello everyone. Today we have you, Yuan, giving talk on Newton Jian, physics consistent and controllable text-to-video generation via neural Newtonian dynamics. He's from Purdue University, and I'm really looking forward to what you have to share today.
Yeah. Thank you, Professor. Thank you for the invitation. It's my honor to be here to introduce our new work, Newton Gene. Um, I'm Yuan, and this is my personal website if you are interested. So this paper, the full name is Physics Consistent and Controllable Text to Video Generation with Neural Newtonian Dynamics. Um, yeah, and this paper aimed to solve a really core and challenging problem that is physical consistency and controllability in current video generation models. So um, let's start from here. This slide shows today's text-to-video generation models, the SOTA models. Like they can even you can see the videos. They can even they cannot even understand or generate the really simple videos like the apple falling, just like our real world dynamics, real world gravity acceleration like that. And this slide also point out the same the same issue by this paper here. Um, the physical consistency, like the color, like the milk label here. So, hmm. and other research, other survey papers, they also point out the overall performance of current video models. They calculate like the physics IQ or um, evaluate the physical performance for different video generators, and you can see um, current video generation current nowadays video generators, they always have a really maybe not good performance. Only a few videos they have a not so bad physical appearance. So um so like actually we humans, I mean the modern science. Well, actually, we spend centuries of observation to find some really fundamental scientific laws. Like here, a few hundred years ago, we understand how the gravity perform and we write these laws in some equations. And here, we need to ask one question for the generative AI domain. That is, can generative AI also learn the concept of time and physics? And before we understand this problem, we should we should go through why current generative models they fail on physical motion. So here, I list the conclusion for our from our community. The reason here is because currently almost all video generators they are purely data driven. That means they are only trained on a lot of videos. And these videos, when they train these models, they only optimize the pixel level likelihood. They just calculate the L1 or L2 loss between the ground truth and the generated videos. Um, and in this way, um, but actually, the training data cannot be infinite and cannot cover every dynamics, every motion. So that means when these models face out of distribution scenarios, then they will usually fail to generalize. They cannot find a similar cases they have learned before So they will just give you a not good guess of what will happen in the auto distribution scenarios. Um, and we know this fundamental reasons why they fail. Then here is our really straightforward solution. That is, um, probably we need to incorporate the physics into current data-driven approaches. So this slide shows this high-level idea. Sub-figure A is current purely data-driven generation. This will give you some low bias because they are real-world videos. But and these videos don't have physical labels, but they will have some poor auto distribution performance. And sub-figure C is some physics-driven reasoning approaches. Maybe here I just say this is reasoning. You can see this is just more physics, and this physics um, will have some high bias because they are usually simulated or some idealized cases, and this one needs some physical labels, and but they have really good out of distribution performance because they cover the fundamental things. And if we can combine these two things, then probably we can have a model which have low bias, only a few physical labels, and they have good out of distribution performance. And here is our high-level framework in the Newton gene. X is the input text or images, and G is the video generator here. And P here is a physical loss. Here we caught neural Newtonian dynamics. It's a neural based physical engine. You can think like that. And this slide shows the overall or very detailed framework. This is a little confusing or complex to understand, but I will decouple this big framework into a few steps, and you can follow easily. So um, so before we introduce more, we need to ask one thing. That is how to model the dynamics in a general or unified ODE. Because from this is a knowledge actually from our high school, right? High school physics. That means we can write some equations, the dynamics equations, um, to represent the dynamics for the acceleration, deceleration, propeller motion, or something like that. But here, because we want to cover as many as possible dynamics, I mean the fundamental Newtonian dynamics, acceleration, deceleration, rotation, or maybe something else. Uh, we need to when we build the neural Newtonian dynamics, we need to we want to cover as many as possible dynamics or ODEs. So to answer this question, we have a few key designs. The key design one is um, how we um, how we the key answer one is we should include as many latent physical states as possible. So uh, here for every I mean for every dynamics for every OD actually we only need to consider a few parameters, physical parameters, like the XY is a 2D location, VXY is speed, theta omega is angle related things, and SLD is shape related things. It can cover like the deformation or something some non-rigid non-rigid motions. um and the short answer two is we is our neural Newtonian dynamics model design. This model covers consists of two parts. The part one is a linear neural OD. This part will cover the major contribution of for different dynamics. So and the other part is a residual MLP. This part will cover the nonlinear part or some variation or some noisy dynamics. How to understand this design? Let me take an example. Like if there is a real world dynamics shows something a parabolic motion with the air friction, right? And this linear neural D will tell you what is the acceleration along the x and y direction. And the residual MLP will tell you the air friction or some noise. I mean, when you capture some videos, you probably have some noise caused by the camera, caused by the exposure time like that. And this design will can cover a lot of things. So and and this is this 2 points is design for our core part ND here. And but how we train the ND, firstly we want to train this ND from some videos. These videos here we called physics clean videos. And physics clean videos, that means we don't need so much unrelated information like the texture, like the background, because we don't care that. We only care about the necessary foreground dynamics here. So in practice, you can build these physics clean videos in two ways. One is collect some real world videos by our camera, but this approach is too time consuming and it's not so easy to build. We also do some experiments in our paper, and we found this one is not the best one compared with the second approach. That is our simulation. We can actually do some real simple simulation based on some physical rules or the equations you write. You write for everything. This equation could come from our knowledge. Also could be some you just write something here. And here I take an example here like the gravity pendulum or bounce. And this is for the training data. And the and from this training data, we need to extract the physical labels, physical states from this data. And here is actually the hardest or easiest part in this project, in this paper. We actually try different ways. Firstly, we try to build an end-to-end. That means the input is videos and the network, and the output is physical states. And we train this model for a long time, but finally we found this one is not easy to achieve the good performance. And and finally we use a much simpler way to finish the part. That is, we use some we use SAM2. That is a video segmentation foundation models. And also we plus some hard decode to get the physical labels here. Okay. Once we have the labels, then the left thing is self-supervised training for the AND. What is the idea here? That is, we already have the so here is a video. And from the above approaches, we can have the each frame's physical states, physical parameters for each frame, and and we pick up or we feed the first frame physical state to the ND here to our neural dynamics engine dynamics model here ND here, and this ND will predict the will predict the following times or following frames physical states. And we just calculate the loss between the ground truth and the predictions by ND. And and this one is really fast because we only need to optimize a few parameters in the ND. That is the MLP parameters and some linear OD physical parameters. It's really efficient. Um, so um, stop here. We already we can use a few physics clean videos, and from this physics clean videos, we will have the trained neural dynamics engine, the ND here. Um, we have this. Then what will happen next? That is only the inferencing. Uh, so so you can see this pipeline here. This is our inference pipeline. Firstly, um, this ND here, the learned neural dynamics here. We also feed the physical prompt. This physical prompt will tell you how big is the world size, what is the nearest objective or the foreground shape, and what is the initial position velocity of this foreground, and uh, and we will parse this physical prompt to get the initial physical parameters z0 here, and the and we will feed the z0 and the following term to our learned neural dynamics models here, and this will predict the future, the corresponding physical states. Like this will tell you what is the future location or speed of the objective in the future in whatever time, right? And and here we also at the world setting here to do some initial rendering. Oh, sorry, here is some issue here. To do some initial rendering to get these things here, the foreground things here. Here we call the optical flow here, and with this rendered optical flow, we will we will have the warped structure noise. And this structure noise plus the scenario prompt, they are fed into the motion controlled video diffusion models. Here we actually use a go with the flow. Um, Here actually we use a go with flow framework, the motion controlled diffusion models here. And this will finally give you the final outputs, the final videos, which obey the same foreground dynamics, the same foreground motions. So you can um, here this is a flow, the information flow. But here I want to emphasize there is a really key design. That is, we in this framework, in this inference pipeline, we can decouple the physical things and the appearance. How to understand? Like the physical prompt here and our ND here is only responsible for the dynamics, only physics, only tell you what is the evolution of the foreground, and the other thing, the other part is a scenario. So this is only controlled by this is controlled majorly controlled by the video diffusion models here. So we send the same prompt here, and actually the video foundation model here is more responsible for the appearance. They will we will give you a really detail rich and some background information. So here we call this is only appearance. And okay, then okay. So in this slides, I show some videos. This is a summary video here. Like we can deal with linear dynamics, circular dynamics, 3D motion effects, deformation, size changing, and some hybrid motions. In this paper, we actually show more than 12 different dynamics, and and the other core part in our paper is we offer the prompter controllability capability. This is actually the first time in the video diffusion models. So uh, you can see here this slide show they have the same prompt, but they have different initial parameters, initial conditions, and this will give you diverse outputs. And the other case is here the two videos they have the different scene prompts, um, but they have the same conditional parameters. And these two videos they are consistent in terms of motion. So these two things we call the parameter controllability. And also this slide also shows the same thing. But here we do some evaluation here. Like you can see our location or our speed is more consistent, like just like the real dynamics. And the previous models like the Sora, you can see their location and their speed is not consistent. It's just weird. It really weird. And here is more slides for the comparison, like the uniform motion, acceleration, deceleration, uh, parabolic motion, 3D motion effect, slope sliding, circular motion, rotation, and some complex or hybrid motion here, both parabola and rotation, and dumped um, oscillation, size changing, deformation. So here, I want to emphasize like our Newton gene can actually control really precise shape. Like here, I mean, uh, this shape should not be the rectangular shape generally, but here we um we choose this shape because we want to say, oh, our model can decouple the dynamics and the appearance. So this is not affected by rich press. Like this shape should be a near round shape. Okay, I think that is technically part of my of Newton gene paper. Um, okay, sorry.
Thank you so much for the presentation. It's super interesting paper.
Yeah.
So you're combining the physical modeling with the video generation.
Yes.
I wonder about generally two questions about
Mhm.
future directions, I guess. So one is about multiple objects. How do you extend this to multiple objects?
Oh, great question. Uh we actually did some initial experiments. We can also deal with multiple objectives, multiple foreground objectives. The only difference here is this time you not only have one objective initial parameters, you probably have different numbers, and this will predict the two different um, sequence, and this two different sequence will be rendered in two different maybe different optical flow here, but they are within the same frame, and the reminiscence is still the same.
I see. Have you tried it?
Yes, it's okay. It's okay. Yeah.
It's okay. Okay,
Yeah.
that's really great to know. That's very encouraging. Another question from my side is how well does NND generalize beyond the training data?
Um, it is really good actually. In the paper, we draw some. Sorry, I don't have the figure here, um, but in but in the paper we draw some line. Um, the ND, the prediction for the trained ND is really accurate, and we draw two lines. One is the ground truth lines, and the other one is the prediction from the ND. They are really close. That means it learns. The performance is really good, nearly perfect.
even for out of distribution.
Auto distribution. Sorry. Here, I want to explain like actually R&D. This is a model, right? This is an architecture here, and for different dynamics, we actually need to train different times.
Mm,
You can think this is actually an MOE architecture, and the same architecture, the same thing in terms of model, but they have different weight for different dynamics. And when you need to, um, so when you need to do inference, you need to choose which dynamics you want.
okay. Then I guess what could be quite difficult is when there are two objects following different dynamics.
Um, I agree with you. Actually, I agree with you. Um, in my understanding. Actually, when you need to inference different objectives with different dynamics, actually, um, this is actually more engineering or more inference part from the inference part. I mean, we need to change the inference pipeline here a little, but
Mm,
for training the ND, it's still the same. Right.
I see. So, okay. At test time, there needs to be some sort of merging mechanism for these two objects somehow.
Yes, yes, I agree with you. And also, there is a major actually a major limitation in the Newton gene that is, you can say our ND is built based on the continuous dynamics, continuous here. The linear, the MLPs are all continuous, so we cannot deal with discrete events like the like the bounce or some multiple interaction, multiple objectives interaction like the collapse, right?
Mm,
This is not possible within current framework because we only care about the continuous part.
hmm. Yeah, but it's good to know the current kind of research frontier. Very
Yes.
interesting. Thanks. And in
Thank
the
you.
meantime, Jian has joined. So, hello, Jian. Are you there? Or?
Or can I leave now because I need to sleep? Go to bed.
Oh, yeah. If you like, yes,
Yeah.
please
Yeah.
go ahead and take some
Uh-huh.
sleep. Thanks for joining super early. I can
Thank you so
manage
much.
the rest of the session.
Thank you so
Thank
much. Have a
you.
great
See you
day.
again. Bye.
Bye.
So, hello, Jan. I sent you an email like 30 minutes earlier because usually the session is supposed to be kind of co-hosted by the speaker. So when the first speaker speaks, the second speaker introduces the first speaker and vice versa. But I guess this time, I mean, this is not super obvious to all the speakers. So sometimes it just goes like this, right? The second speaker joins only after 30 minutes, which is then fine. I mean, I can also host the talks. So, which is what I'm going to do for the second session. So, I'm going to host your talk. And
Um,
are you ready to give a talk?
uh, Sorry for I have um just finished my PhD defense, so
Oh, I see.
I had
Okay.
little time. I have
Congratulations.
little time to prepare my the slides for this meeting. Maybe.
So, in principle, it's fine to not have any slides.
So um can I talk about the paper directly referring to the paper itself?
Yeah, yeah, you can do that.
Just like okay. Uh, I mean, the 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 talking about 30 minutes.
So please finish the talk in about 15 minutes, and we can do some Q&A afterwards.
15 or 30 minutes?
15 minutes and not 30
15
minutes.
minutes? Okay. Just for for this meeting, I'd like to share the recent paper about neural process. The title is neural brain process from our team. And just briefly introduce myself. I'm Jian. I'm from South China University of Technology. And I'm in Guangzhou. And next week I will like to reconnect IP to continue my postdoc research. My research interest in stochastic process machine learning and probabilistic machine learning, like Gaussian process, like generative models, and so on. Yeah, and these are my quarters. This paper, Jian Liu is also in a master in South China University Technology, and my later in reconnect IP is Diffusion Zhang. And John Beasley, Professor John is also my core advisor in Columbia University, and my direct advisor is Drew Zhang. Okay, Professor Zhang. This paper just it's just a submit and in a cap, and you can search this title. And your bridge processes. Sorry for that. I haven't enough time to prepare my slides, because I just must pay much attention to my PhD defense, and I've just finished it, and just received the email that said last month, like coming to present this our recent research result about stochastic process in machine learning. And for this paper, we focus on learning a stochastic function. This is very popular and very harsh, very popular in probabilistic machine learning. And some classical model like the Gaussian process, neural process, and so on. We study this historical and classical papers, and we also learn some diffusion models. I mean, we can use the experience about training the diffusion models to help us to train the stochastic function much more accurately and fast. I mean, so the title is neural bridge for diffusion bridge models. Like very recent models in diffusion generative models. The baseline is we consider baseline neural diffusion process in research top avenue like I say like SML. I remember just the year before last year, maybe 2023, SML has a good result. It has good result in neural stochastic function modeling, and our intuition is to prove this model by the bridge models, because neural diffusion models of these recent models, although it enhanced expressively through a large diffusion, but they rely solely on conditional single thing that denoising network can result in a weak input coupling from an unconditional forward processing semantic mismatch as a diffusion endpoint. So this paper's emphasizes more on the endpoints matching, how to match it to endpoints in the diffusion model for stochastic function model. So in this work, we propose neural bridge process. We mean this relatively a narrow method for modeling stochastic function. In this model, the input x dynamic exactly depend on x, not only for the denoising network itself, but also for the but also for the forward modeling. So it's emphasis constraint paths. We just emphasize forward paths that strictly cameras as the supervised target, and we evaluate these models on three classical tasks on mental learning. Mental learning is like a synthetic data is easy and the image is regression. These three tasks are focusing on the mental learning task. And let's review the background of the neural process or function modeling. It's like equation 1 or 2. 2 is classical modeling or machine learning task. X C is for content, and the YT or XT is for the target, for our target, and we want to use the content X, Y, and the target of X to predict the distribution of the target Y, and this the Latin variable. Okay, and this the change of the distribution of the probabilistic rule of the relation. And this is a traditional method like the album. We can use this one to compute the bound for log likelihood. And this is the series of the neural process models are very popular, highly referred by many neural process stochastic function paper. And recently, as the diffusion models rise in machine learning or deep learning task, some orders also use this the idea of diffusion models in neural process stochastic function modeling. They call this model neural diffusion model, neural diffusion process. The Z.2 is a review of the neural process, neural diffusion process. They mean the wide neural process effectively combines neural network with stochastic process for future learning. They relies on simple latent variable limits the ability to capture complex multimodal diffusions. So the NDP, neural diffusion process stresses introduces stochastic trajectories modeling in the mapping from inputs to output as a large diffusion process. This is the chain, Markov chain, just like diffusion. Diffusion process to model the network in the function modeling. It's like they just use forward diffusion process incursion. And three, like this. I think all of you are very familiar with these incursions. It's just classical incursions in DiffM and Y1 to Y capture T is a Markov chain in diffusion. In the diffusion process and Y capture T is the purely Gaussian noise, and Y0 is the clean data. Okay, and the forward process is also a noising. If you just put Gaussian noise into the clean data, and we can get Y1 to Y capture T by this Markov chain, and you can use the beta to control the schedule of this process. And the various process we can also review like DiffM. You can use mu and filter beta. Okay, the mu theta is a neural network, just like a UNet. Classical is UNet or a transformer network. Okay, and the order of DiffM, they derive the result the reverse mu theta, just like equation 6. Okay, and they are very familiar with this equation and this result. Okay. And you can multiply from 1 to T, and you can multiply this, or by 1 minus beta is, and you just you can use the DDPM loss, the score matching or the score matching loss to train this to train this denoising network. Okay, and their motivation is they can use the training loss, the training loss of the DDPM to train. It can also be use this loss to train the neural process. Okay.
So now we used 15 minutes actually, so we need to speed up a little bit to kind of have some Q&A at the end, if that's
just
okay. Yeah.
20 minutes, 30 minutes.
So yeah, we recommend
30
usually.
minutes left.
Sorry.
That's how many minutes left I can present this work?
Ideally, we wanted to have just 15 minutes of presentation and have some Q&A, but now we have spent 15 minutes. So, I mean, the hard limit is in 15 minutes. Well, actually, in 10 minutes. So, please try.
Present this work faster. So our idea to improve this work is to use the idea bridge process, and we just plus additional 10. We name this a bridge term, a bridge term gamma t x, and the gamma t is designed as incursion 9. Use the SNR stair function. Okay, and the intuition is when the t is more less than the capture t, and gamma t is opposed to 0, and the process approximates standard diffusion. And when the t post capture t and the gamma t opposed to 1, and the trajectory increasingly guided towards the desired target. But in the valid neural diffusion, so our baseline, they did not guarantee this good good definition. Okay, and we use this these core ideas to guarantee the endpoint match. Endpoint match. I mean, you can use you can model a valid function modeling from x to y, but in the valid NDP, and just start from the pure noise to the target. So we consider this may raise some concern about endpoint or weak supervisation. So this introduces stronger gradient signals and coherent trajectory optimization. And we use some mathematical formula to compute this, or how to solve this the reverse process, like the incursion 16, and this very we surprised surprisingly found that the results is solely we can solely add a bridge correction to correct this the reverse to have a good result or valid result about this braid process. So this is not a desired result, but also a result by our mathematically direction. So we think this innovation is very regularly recognized. And the network is we just use a network from the baseline to design our denoising network. The CT is solved like the Gaussian 17, and the training object is the same. But the YT we use YT is the relation of YT and X with additional direction of this in our NDP models. This is also mathematically result. So we think we can see some research about our paper, and this is numerical research about our models against baseline, NDP, GNP, and some neural process baseline like this, and like log text likelihood in toy GP synthetic a result, a simple GP model. And also we did real world experience in EEG signal regression task. And we make the three sub tasks like the instruction and forecasting. And we also compare our message with against some recent baseline. And also in image regression task, like this, a classical image regression, image regression task, you can crop a clean image, and also our model can cover it by our models. And just this is SC result. This is the orange lines is ours. We implement our task on server A 13.2 and server A 16.4. And also we have some direction in our appendix, but due to the time and the space limit, you can if you are interested in our paper, you can find your URL on archive and also in email with our team. This will thank you. And also you can you can propose useful suggestion or comment. And this all.
Thank you so much for your great presentation. I have one question to follow up. So, can you tell me a little bit about, so I guess your main argument is that the endpoint should match, right? And the main kind of practical reason for that is let's say you have less data and like sparse data. You want to make most of the given data points. Is that right?
Sorry, I don't understand. Do you mean endpoint match, the focus on endpoint match, which incursion, or you focus on
So, yeah.
you
Mhm.
understand the idea of our paper. It's just we rightly use endpoint match. This is our what we emphasize.
Mhm. So you mentioned this.
And
What I'm trying to do is to connect the endpoint match problem and the practical benefits. I think as part of practical benefit, you mentioned sparse training or training with sparse data. Is that
yeah,
right?
you are
So
right.
I, so my question
Just
is, how do you connect these two concepts here? So one is endpoint matching, and the other one is sparse data with like training with sparse data. So how are these connected with each other?
training with sports data. Um, we think um, because in the real world data, the task may be very the data may be very complex, and the original NDP besides just use pure noise. This stuff from pure noise to generate the label, the target of this supervised learning, which um, our models match rightly from the endpoint is our the observation that we can get from and we think we should use these observations to try our best to use this as a surprise signal. So um, so we think this may help to solve sparsely sparsely observed data. Um, because many because the original baselines is just very little signal, very little signal that denoising their reverse network also. But our models directly model the supervised signal in the forward process. So we think we can use enough information of these signals to correctly solve our problem to improve their result.
Okay.
But we think this may the future work may use more mathematic intuition to quickly explain this this series of experimental results to better present our paper.
hmm Okay, thank you. Anything else that you have to say? Otherwise, um, I wish to thank you again and close the session.
So it's this all. I can close this down.
Okay, so you can close.
Okay, screen. Okay. Thank you,
All right.
Professor.
Thank you so much for coming and presenting.